Right now, there is next speaker is Manuel Mancini, and we'll talk about the representability of actions for non-associative algebras.
Okay, good afternoon to everyone. Thank you, Beppe, and I want also to thank all the organizers for inviting me and giving me the opportunity to talk here at Itaca Fest. This is a joint work with Josep Rox from Valladolid, Alan Cigoli from Turin, Xavier Garcia Martinez from Vigo, Beppe Metere from Milan, Tim van der Linden and Corentin Vienne from UC Leuven. So I want to start by recalling a property of the category of groups regarding actions or split extension. That is the starting point of this talk. So in groups, if we take an action, internal action of B on X that can be described as a map from B times X to X in this way, so we denote by B times X the action of an element B on an element X, then given such an action, we can construct the semi-direct product associated with the action. That is the group defined on the Cartesian product B times X, where this is the multiplication. So the multiplication is determined by the action, essentially. And moreover, we can also associate with the action the split extension given by the semi-direct product, where I1 and I2 are the canonical inclusion on the first and the second component, and pi1 is the projection on the first component. So if we start with an action, we can define a split extension, but we can do also the converse. Starting with a split extension, we can define an action of the group B that is the co-kernel of the split extension on the kernel X, and the action is given essentially by the conjugation of beta of B and K of X. So we are conjugating B and X, but inside the group A. And one can prove that there is a bijection between actions of B on X and isomorphism classes of split extension of B by X. Moreover, it is known that in groups, action or split extension are in bijection with the homomorphism from B to the group of automorphism of X. Indeed, if we take a split extensions, then we can define an homomorphism from the co-kernel to the group of automorphism of the kernel, where the automorphism phi of B acts on X as the conjugation again, and again one can do also the converse. So if one take an homomorphism from B to out of X, then one can define a semi-direct product and then a split extensions. And so our goal is to study this property, to extend this property of the category of group to a bigger context. And one good candidate is the context of semi-abelian categories, because semi-abelian categories were introduced in order to provide a categorical setting which would capture algebraic property of categories of algebraic objects like groups, rings, and algebras. And indeed, semi-abelian categories generalize the property of the category of groups as abelian categories do for abelian group. I recall that a semi-abelian category is pointed, bar-exact, protomodular with finite coproducts, and in any semi-abelian category, we can define the notion of split extension of B by X. So if we take two objects, a split extension of B by X is a diagram of this kind in C, where the composition alpha beta is the identity of B, and the pair xk is a kernel of alpha. When we fix an object X in C, we can define the contravariant functor of split extension with kernel X, so split extension by X, that maps any object B in C to the set of isomorphism classes of split extension of B by X. And as it happens in the category of groups, we have a natural isomorphism from the functor of split extension by X and the functor of internal action on X. Here I will not describe what is an internal action, and in our context, that is the one of non-associative algebras, it is better to work with split extensions. So the first tool that we have to study actions is the notion of action representability that was introduced by Bourseau, Gianelizza, and Kelly in 2005. I recall that a semi-abelian category C is action representable if for every object X in C, the functor of split extension by X is representable. So this means that we have an object that we denote by bracket x, and we called it the actor of x, and a natural isomorphism between the functor of split extension by x and the functor of morphism in C with the codomain the actor. And the prototype example of action representable categories are the category of groups, as we saw in the previous slides, where the actor is the group of automorphism of X, and the category of Lie algebras over a commutative ring R, where the actor is the Lie algebra of derivation of X. The problem is that there are not a lot of concrete examples of semi-abelian category that are action representable. And indeed, it was proved that this notion is quite restrictive. For instance, in the context of variety of algebras over an infinite field with the characteristic different than 2, it was proved that the only action representable variety are the variety of abelian algebra, so vector spaces with a trivial multiplication, with a zero multiplication, or the variety of Lie algebras. And 2 years ago, George and Elise introduced the notion of weakly action representable category, which includes a wider class of semi-abelian category, as we will see. So essentially, we have the same notion of before, but now there is just a monomorphism of functor from split extension by X and morphism in C with the codomain that is an object of C that depends on X. Here it is denoted by T, and it is called a weak actor. The pair T tau is called a weak representation of the functor of split extension by X, and I want to observe that in general, a weak actor is not unique like the actor. Moreover, when a morphism comes from a split extension, we will call it active morphism. A first example of a action representable category, of a weak action representable category, is any action representable category, where a weak actor is the actor, and every morphism is an active morphism, and so tau is a natural isomorphism. George and Elise gave another example in his paper. He proved that the category of associative algebras over a field F is weakly action representable, with a weak actor that is given by the associative algebra of bimultipliers of X, where a bimultiplier is a pair of two linear endomorphisms of the algebra X, where the first one is a left multiplier, and this is expressed by the first equation. The second equation tells that the second one is a right multiplier, and together they are compatible, where compatibility is expressed by this kind of associativity between X, F, and Y. Moreover, last year, together with Alan Cigoli and Beppe Metere, we proved that the category of Leibniz algebras over a field F is weak action representable. I recall that Leibniz algebras are a non-skew symmetric version of Lie algebras. They were introduced by Lodin in 1992. And Lodin, in his paper, defined the Leibniz algebra of biderivations in order to generalize the notion of derivation for a Lie algebra. And we proved that this Leibniz algebra of biderivation is a weak actor. And again, I want to observe that we have again an algebra defined on a subspace of two copies of a linear endomorphism of the algebra. In general, it is not true that every variety of algebra is weak action representable. For instance, if one considers Jordan algebras that are commutative algebra with the Jordan identity, one can prove that the category of Jordan algebra is not weak action representable because every weak action representable category is action accessible, and the category of Jordan algebra is not action accessible. So our aim is to study the notion of weak representability of actions in the context of varieties of non-associative algebras over a field. So we fixed such a variety over a field of characteristics different than 2. And for us, I want to recall that a variety is a class of non-associative algebra that are vector spaces over a field F with a bilinear map, a bilinear multiplication that satisfy a certain set of polynomial identities that are the identities which define the algebra. In our work, we suppose that these identities are multilinear, and we call such a variety operatic. This is not too restrictive because in characteristic 0, for instance, every variety is operatic. Then we have to suppose that the variety is action accessible because otherwise it is not weakly action representable. And for varieties of algebras, it is equivalent to saying that this is an object category of interest, or it satisfies the lambda mu rules. This means that we can choose 16 constant in the field f, such that we can express both x, y, z and y, z, x as a combination of multiplication between x, y, and z, where x is never isolated, in the sense that x is always inside the bracket in the second members. And these are identities of B. And we have to fix a choice of the lambda mu rules, because for the same variety, we can have different choices of the lambda mu rules. Then we have to fix a set of multilinear identities which determine the variety. And what we look for a vector space, E of x, which is, again, a subspace of two copies of linear endomorphism of x, and it contains the space of left and right multiplication for element of x. And we want that this vector space allow us to describe actions, in the sense that we want to endow this with a bilinear partial operation, because we will see later that in general what we obtain is just a partial operation on x times x. And in such a way we can associate in a natural way a morphism of partial algebras, where the domain is an algebra of V, is an object of V, and we have to do this with a split extension of V by X in V. So this means represent actions. And I recall what is a partial algebra. So for us, a partial algebra is just a vector space where the bilinear operation is not defined everywhere. It's a bilinear partial operation. So it is defined in the subspace of X times X. And a morphism of partial algebra means that we have a linear map, and the products are preserved when they are defined. But since we will consider morphism where the domain is a total algebra, because it is an object of B, so we have that this expression is always defined, and the images of this morphism are object of the variety, because the category is closed under quotients and the images are quotients. So we want to study split extension in our variety, and we can describe our split extension as semi-direct products, where the action of B on the X is defined by a pair of bilinear maps that are these two, B star X prime and X star B prime. And these two bilinear maps are uniquely defined once we fix the split extension, because they are defined using the maps beta and k of the split extension. But we can do also another thing. We can forget about the split extension, and we can start with this bilinear operation defined on the direct sum of vector spaces B plus X. And we want to know when this bilinear operation define an algebra structure in V for B plus X. And we have that this happens if and only if all the identities of the variety V that we fixed at the beginning are satisfied when we substitute to the variable alpha 1, alpha k, either element of the form 0x or element of the form B0. The resulting algebra is, of course, the semi-direct product, and we will use the following notation. B star x will mean B0 times 0x, and analogous for X star B. Now we can define the partial algebra E of x. We start with the vector space structure. So the vector space will be the space of all pairs of linear endomorphism of X, which satisfy all the identities of V when we substitute to the variable for exactly one index J from 1 to K, an element that here we denote by F, and now I will explain what it means. And for all the other variables alpha T with T different than J, we put element of X. We have to do this for all the choice of J from 1 to K. And if I have an expression of the type Fx, so F is on the left, then this means that I have F star X. And the same if F is on the right. So this will mean X star F. Then I have to define the multiplication on E of X. And I start with a bilinear map defined on E of X times E of X into and X square, that is defined using the lambda mu rules that I fixed at the beginning. In general, this does not define an algebra structure because this is not an internal operation, but it can happen that this is an internal operation. For instance, in the variety of associative algebras, E of X is exactly the associative algebra of bimultipliers of X. And in the variety of Leibniz algebra, E of x is isomorphic to the Leibniz algebra of biderivation of x. So in both cases, E of x is the weak actor. Then I want to observe that with the E of x, we can give a new characterization of split extensions, because a split extension can be defined as a linear map from B into the vector space of E of x, where in such a way, all the products that are preserved by the bilinear map, in the sense that I know how to compute the action of a product BB prime if I know how B and B prime acts. And moreover, for having a split extension, I need that all the identities of V are satisfied again when I substitute to the variable either element of the form B0 or element of the form 0x. And so again, I will have expression of the form B star x or x star B. Now I can define the partial operation. And how I can define it? I can restrict the bilinear map that it is not an internal operation to the pre-image of the inclusion of E of x inside and x square. And so now I have a partial algebra. And by considering the forgetful functor of the variety V inside the category of partial algebras, I can prove our main result. So we proved that for every object x in the variety V, there exists a monomorphism of functors from the functor of split extension by x and the functor of morphism of partial algebra, where the domain is a total algebra, is an algebra of V, and the codomain is the partial algebra E of x. So this is like a weak representation in the sense of Georgian elides, but here the home functor is taken in the category of partial algebras. Moreover, we know how to determine if a morphism from B into E of x comes from a split extension. So we have to check that all the identities of B are satisfied as before. In the special cases, as it happens for associative algebra or Leibniz algebra, where E of x is an object of B, then I have a weak representation. And when V is a variety of commutative or anti-commutative algebra, so this is the reason why we suppose that the characteristic of the field is not 2, because we want to distinguish these two cases, then we can describe E of x as a subspace of just one copy of linear endomorphism of x. And also the bilinear partial operation is easier to describe because the lambda mu rules reduce to just one equation with two coefficients alpha and beta. We call E of x an external weak actor because it is like a weak actor, but it is external from the variety V. The pair E of x tau an external weak representation, and when tau is a natural isomorphism, E of x is called an external actor. So now I want to give some example to understand that in general we obtain just a partial algebras. Okay, but I want to start with a trivial example, abelian algebras, so that are essentially vector spaces. The multiplication is trivial, and so we obtain that E of x is 0, is the zero algebra, and so it is an abelian algebra and it is the actor of x. For commutative associative algebra, I obtain an external actor, but it is just an associative algebra, it is not commutative. And this is the associative algebra of multipliers of x. So in this case, this is not an object of the variety. For Jacobi-Jordan algebras that are commutative algebras with the Jacobi identity, I obtain just a partial algebra that again is an external actor, and it is the algebra of antiderivation of x. For Lie algebra, I obtain the actor, that is the Lie algebra of derivation. For two-step nilpotent commutative algebras, I obtain just a weak actor because this is an object of the variety, because this is an abelian algebra, so this is a very special case. And then another example, alternative algebras that are a generalization of associative algebras. In general, this is not an operatic variety, but when the characteristic is not of the field is not 2, I can multilinearize the identities, and so the variety is operatic. And in general, I obtain a C of x a partial algebra. But when x is unitary, because alternative algebras can have the unit, then E of x reduces to x. And then I have that E of X is an object of the variety. And moreover, since it is isomorphic to X, I obtain that the monomorphism is an isomorphism. And so X is the actor of itself. This means that unitary alternative algebras have representable action, and in particular, we can apply this result to the algebra of octonions. Now, I want to focus on the case when E of X is not an object of B. What we can say when E of X is not an object of B? In general, we cannot conclude that the variety is not weakly action representable. For instance, if I consider Leibniz algebras, I said before that we proved that the Leibniz algebra of biderivation is a weak actor. I was a little bit imprecise because E of X for Leibniz algebra is isomorphic to the to bider of X, so biderivation of X, just as a vector spaces. The fact that this is an isomorphism of algebras, of Leibniz algebras, depends on the choice of the lambda mu rules. If I choose the lambda mu rules in the standard way, so as Leibniz algebras as usually defined, I obtain a multiplication on bider of X that define a weak actor in the variety of Leibniz algebras. But if I change the choice of the lambda mu rules, and here I'm just changing this last term, one can prove that these two equations define the same variety. But with this choice, the multiplication that I obtain on E of X, that is always isomorphic to bider of X as vector space, define just a non-associative algebra structure. And so in this case, E of X is not a weak actor, but it is not true that the variety is not weakly action representable. Another example, commutative associative algebras. With commutative associative algebra, with the standard choice of the lambda mu rules that is given by the associativity, I obtain that E of X is an external actor, is the associative algebra of multipliers of X. So again, we have an object that in general does not belong to the variety because this algebra is not commutative. And here, if I change the choice of the lambda mu rules, I never obtain a commutative associative algebra. So one can think that the variety of commutative associative algebra is not weakly action representable, but the answer is no, as we will see. So at first, I want to recall that the representability of action for this variety was studied by Borsoggian and Lizenkelli in 2005, and they proved that actions on X are representable if and only if M of X is commutative. But since it is easy to find example where M of X is not commutative, one can conclude easily that the variety is not action representable. But what about weak action representability for this variety? For answering to this question, we have to introduce the notion of amalgamation. So I recall that for a diagram in a category C, an amalgam is a monic cocon. So it is a cocon which is a monomorphic natural transformation. And a category with push-out C has the amalgamation property when each span of monomorphism in C admits an amalgam. So this means that if I have a push-out square of this kind, where S and T, these two arrows, are monomorphism, then also the other two arrows of the diagram are monomorphism. There are different examples of categories that that have the amalgamation property. For instance, groups, Lie algebras over a field, in this case, and Boolean rings. And Boolean rings can also be seen as algebras over F2 with the identities with the identity x squared equal to x. So Boolean rings can be seen as an example of a non-operatic variety of algebras. And in the same paper of Borsoggian and Lizenkelli, it was proved that this category is action representable. And there are also examples of categories that don't have the amalgamation property. And for instance, commutative associative algebras and associative algebra don't satisfy the amalgamation property, don't have the amalgamation property. But how to connect amalgamation property with the representability of actions? Borsoggian and Lizenkelli in the same paper proved that if for an object X in a semi-abelian category C, if the action on X are representable, then the amalgamation property holds in C for the Plato-split monomorphism with domain X. And I mean monomorphism with domain X which are the kernel part of a split extension in C with kernel X. The converse in general is not true. For instance, if I consider purely non-associative algebra, so vector spaces with a bilinear operation that in general does not satisfy any identity, then the amalgamation property holds, but the action on a non-associative algebra X are representable if and only if X is an abelian algebra. The converse is true in special cases, such as when C is an Orszag category of interest. And for instance, in this frame, we find all the variety of algebras that are action accessible. Now I want to link the amalgamation property with the weak representability of action in the case of commutative associative algebras. So I observe that the external actor M of X is an amalgam for the diagram of all commutative subalgebras of M of X. But this is an amalgam not in the variety of commutative associative algebra. It is an amalgam in the variety of associative algebras. And the new question now is, this diagram, that is a diagram in the variety of commutative associative algebra, admits an amalgam in the variety of commutative associative algebra, and we can reduce our question whether the variety of commutative associative algebra is weak action representable or not to this new question about the amalgam, because we prove that a weak representation exists if and only if such an amalgam exists in the variety of commutative associative algebras. And then we reduce this problem to a smaller problem, that is to find an amalgam just for a span of commutative associative algebras. And we prove in particular that if a span of commutative associative algebras has an amalgam in the variety of associative algebras, then it has an amalgam in the variety of commutative associative algebras. We extended these results to arbitrary diagrams of commutative associative algebras, and since the diagram of all possible commutative subalgebra of M of X is an example of a diagram of commutative associative algebras, then, in other words, we prove that the category of commutative associative algebra is weakly action representable. But for every choice of the lambda mu rules, the external weak actor is not an object of the variety. So what is the difference? The difference is that the weak actor that we find in this theorem is obtained using a tensor product and then quotients of tensor product. And so it is not easy to compute by hand. While the external actor is just a subalgebra of matrices, and so it is easier to find by hand. And so it depends on what we are doing. Maybe it is better to work with the external weak actor, also if it is not an object of the variety. Finally, we extended this result to a general variety and an external weak actor. But here we have to focus on the diagram of subalgebra of E of X that occur as a codomain of an active morphism, because in the case of commutative associative algebras, we have an external actor, and here we have just an external weak actor. So if an amalgam exists, then this amalgam, that is the colimit of the diagram, determines a weak representation. So I want to conclude just with a few open problems that we have. So at the moment, we didn't find a counterexample of an action accessible variety of algebras that is not weak action representable. So we are trying to understand if the converse of this implication holds in our context or not. Then we would like to generalize the construction of the external weak actor to variety of algebra with more than one operation, for instance, two operations. And we think that it's possible because we already have a positive answer for Poisson algebra and commutative Poisson algebra. And finally, we would like to extend the study of the representability of action also in non-pointed context. And for non-pointed context, I mean ideally exact categories in the sense of Georgian elides. And for instance, the variety of algebras which admits units, for instance, unitary associative algebra and unitary alternative algebra, are examples of either exact categories. And using the external weak actor, we prove that these two categories, either exact categories, are action representable. And so we would like to understand what happens in a general variety of algebras with unit. So this is all. I conclude here, and I leave here some bibliography, and I want to thank you for your attention.
Thank you, Manuel. Thank you for your interesting talk. And so I'm opening my microphone to anybody who has questions or would like to express a comment. Any question? Okay, so we can thank Manuel again, and we have an 8-minute break.
Thank you.
Thank you.